There is a star in the northern sky that breathes, not in the way we breathe, not with lungs or air or any mechanism we would recognize, but it swells and contracts, brightening and dimming over and over like a slow cosmic heartbeat. It has been doing this for millions of years. It was doing this long before the first human looked up and wondered what the lights in the sky might be. And it will continue doing this long after every telescope we have ever built has crumbled to dust. The star is called Delta Cephei. It sits roughly 890 light-years from Earth in the constellation Cepheus, named after a mythological king. It is not the largest star in its constellation. It is not the brightest. You can see it with the naked eye on a clear night, but you would never pick it out of the crowd. It looks, for all purposes, like just another point of light in a sky full of them. And for most of human history, that is exactly what everyone assumed it was. Just another star, steady, unchanging, eternal. But in 1784, a young astronomer in England noticed something that no one else had caught. The star was changing. Its brightness was not constant. Over a period of roughly 5 days and 9 hours, it would swell in luminosity, fade back down, and then swell again. The pattern was not random, it was not chaotic, it was precise, predictable, metronomic, like a clock ticking in the dark, a slow pulse beating through the emptiness of interstellar space. The young man who noticed it was just 19 years old. He had been deaf since childhood, unable to hear the sounds of the world around him. But he could see. He could see with extraordinary clarity. And what he saw in the flickering of that star would eventually reshape our understanding of the entire universe. Not just our galaxy, not just the nearby stars, the entire observable universe, stretching 93 billion light-years from edge to edge. The discovery of Delta Cephei's pulsation would become one of the most important findings in the history of astronomy. It would provide the key that unlocked distances so vast that the human mind buckles under the weight of them. It would settle one of the fiercest debates in the history of science, double the known size of the cosmos overnight, and ultimately reveal that the universe itself is expanding, carrying every galaxy away from every other galaxy at speeds that increase with distance. All of this from a flicker, a gentle rhythmic flicker that almost no one noticed. By the end of tonight, you're going to understand how a single variable star, one heartbeat of light among 400 billion others in our galaxy alone, gave humanity the ability to measure the cosmos. You are going to understand why the rhythm of Delta Cephei changed everything we thought we knew about how big the universe is, where we stand inside it, and whether the seemingly empty darkness between the galaxies is truly void or filled with something far stranger than anyone had imagined. You are going to understand why some scientists call the Cepheid period-luminosity relationship the most important discovery in modern astronomy, and why others argue it is also the most dangerous. Because every error in its calibration ripples outward across billions of light-years, distorting our entire picture of reality. Before we get started, if you love exploring the depths of space as much as we do, take a second to like the video or subscribe. It is a simple action, but it helps this channel reach more curious minds like yours. The story of Delta Cephei is not just a story about a star. It is a story about measurement, about precision, about the long and fragile chain of reasoning that connects us to the edge of everything we can observe. It is a story about a deaf teenager who changed the world, a woman whose work was overlooked and then stolen, and a generation of astronomers who realized, too late, that the universe was not what they thought it was. It is a story about what happens when you build your entire understanding of cosmic distance on a single delicate assumption, and then discover, decades later, that the assumption might be wrong. It is a story about how far we have come and how much we still do not know. The answers are stranger than you think, and the questions they raise are stranger still. There is a thread running through the history of astronomy that connects a garden in England to the most powerful space telescopes ever built. A thread that passes through a basement at Harvard, through the wartime blackouts of Los Angeles, through a photographic plate, with a crossed-out letter and an exclamation mark. That thread begins with Delta Cephei. It begins with a heartbeat, and it leads, ultimately, to a crisis in our understanding of the cosmos that remains unresolved to this day. Now let's begin. To understand what Delta Cephei revealed, we first need to understand a problem that haunted astronomers for centuries. It is a deceptively simple problem, one that a child might ask on any clear night. How far away are the stars? This question sounds straightforward. On Earth, we measure distance all the time. We use rulers, tape measures, laser rangefinders. We bounce signals off surfaces and time how long they take to return. We triangulate positions using landmarks and angles. Distance is something we handle with ease in our daily lives. We know how far it is to the grocery store, to the next city, to the coast. But none of the methods we use on Earth work in space, not at the scales we need them to. The distances are simply too large, the objects are too far away, and for most of human history, we had no reliable way to measure them at all. The stars could have been a few miles overhead, stuck to a crystalline sphere, as the ancient Greeks imagined, or they could have been infinitely far away. There was no way to tell. Consider the nearest star to our Sun, a dim red dwarf called Proxima Centauri. It is 4.24 light-years from Earth. That number, 4.24 light-years, sounds manageable, almost modest, until you convert it into units that carry human meaning. 4.24 light-years is roughly 40 trillion kilometers. 40 trillion. That number is too large to visualize directly, so let us bring it down to a human scale. If you could drive a car at 100 kilometers per hour, without stopping, without sleeping, without refueling, just driving straight through the void toward Proxima Centauri, it would take you approximately 46 million years to arrive. The entire recorded history of human civilization, from the first clay tablets in ancient Sumer to the smartphone in your pocket, spans roughly 5,000 years. You would need to repeat that entire arc of human history more than 9,000 times, end to end, to cover the driving time to our nearest stellar neighbour, and that is the closest star, the easiest one, the one right next door. Here is another way to feel the distance. If you shrank the Sun down to the size of a basketball, roughly 24 centimeters in diameter, the Earth would be a tiny peppercorn about 2.4 millimeters across, orbiting 26 meters away. On that same scale, Proxima Centauri would be another ball, smaller than the basketball, but it would be located roughly 6,900 kilometers away. On a model where the Sun fits in your hands, the nearest star is on the other side of a continent. The Milky Way galaxy, our home, contains approximately 400 billion stars. Some estimates put the number even higher, at perhaps 1 trillion. These stars are spread across a flattened disk, roughly 100,000 light-years in diameter and about 2,000 light-years thick. If you were to fly across the Milky Way at the speed of light, the fastest speed that anything in the universe can travel, the journey would take 100,000 years. Light travels at 299,792 kilometers per second. Even at that speed, crossing our own galaxy takes a span of time longer than the entire existence of modern humans, and the Milky Way is just one galaxy. The nearest large galaxy, the Andromeda Galaxy, is approximately 2.5 million light-years away. The observable universe extends 46.5 billion light-years in every direction from Earth. It contains, by current estimates, roughly 2 trillion galaxies, each containing hundreds of billions of stars. The total number of stars in the observable universe is estimated at something like 200 sextillion, or 2 followed by 23 zeros. These numbers are not just large, they are incomprehensible. They overflow the containers of human intuition. The brain that evolved to navigate savannas and judge distances of tens or hundreds of meters is being asked to hold spans of trillions upon trillions of kilometers. So astronomers needed tools. They needed methods. Clever, indirect methods that could reach where no ruler could. And the first tool they developed was one of the oldest ideas in geometry. It is called parallax. Parallax is simple in principle. Hold your thumb up at arm's length and close one eye. Now open that eye and close the other. Your thumb appears to shift against the background. That apparent shift is parallax. The farther away an object is, the less it appears to shift. By measuring the angle of the shift and knowing the distance between your two eyes, you can calculate how far away the object is. This is basic trigonometry. It works on Earth. Surveyors have used it for centuries to measure the distances to mountains and landmarks. In astronomy, the two eyes are not your left and right eye. They are Earth's position in its orbit at two different times of the year, 6 months apart. In January, Earth is on one side of the Sun. In July, it is on the opposite side, roughly 300 million kilometers from where it was 6 months earlier. That 300 million kilometer baseline is the widest ruler astronomers can use from Earth's surface. By photographing a star in January and again in July, and measuring how much it appears to shift against the background of more distant stars, astronomers can calculate the star's distance. The first successful measurement of stellar parallax came in 1838, when Friedrich Bessel, a meticulous German mathematician and astronomer, measured the parallax of a star called 61 Cygni in the constellation Cygnus. He found that the star's apparent position shifted by about 0.314 arcseconds over the course of a year. An arcsecond is 1/3600th of a degree. It is an almost impossibly tiny angle. To grasp how small it is, consider this. 1 arcsecond is roughly the angle subtended by a single human hair viewed from a distance of 20 meters. Bessel's measurement was a triumph of observational precision, one of the finest achievements of 19th century science. It confirmed what astronomers had long suspected but could never prove. The stars were unimaginably far away. 61 Cygni turned out to be about 10.3 light-years from Earth, roughly 64 trillion kilometers. What is often forgotten is how long it took to achieve this measurement, and how many brilliant astronomers failed before Bessel succeeded. The quest to detect stellar parallax stretched back centuries. Tycho Brahe, the great Danish astronomer of the 16th century, had searched for it and found nothing, which he took as evidence against the Copernican model. If the Earth truly orbited the Sun, Tycho reasoned, the stars should show parallax. Their failure to do so meant either that the Earth was stationary or that the stars were unimaginably far away. Tycho, unable to accept such vast distances, chose to reject Copernicus. He was wrong, but his logic was sound given the evidence available to him. The distances really were unimaginable, and the parallax angles really were too small for his instruments to detect. For 2 centuries after Tycho, astronomers continued to search and continued to fail. The parallax race of the 1830s was one of the most intense competitions in the history of science. 3 astronomers pursued the prize almost simultaneously. Bessel targeted 61 Cygni, Thomas Henderson at the Cape of Good Hope Observatory targeted Alpha Centauri, and Friedrich von Struve in Russia targeted Vega. Bessel published first, in 1838, but Henderson's data, analyzed later, yielded a result for Alpha Centauri that was also correct. All 3 measurements confirmed the same staggering conclusion. The nearest stars were trillions of kilometers away. The universe was vast beyond anything previous generations had conceived. And from that moment forward, the problem of astronomical distance, once an abstract philosophical puzzle, became the central practical challenge of observational astronomy. But here is the problem with parallax. It only works for nearby stars. As the distance increases, the parallax angle shrinks. Beyond a few hundred light-years, the angle becomes so small that even the best ground-based telescopes cannot measure it reliably. The atmosphere shimmers, the star images blur, and the tiny shift is lost in the noise. Even space-based telescopes have limits. The European Space Agency's Hipparcos satellite, launched in 1989, could measure parallax angles down to about 1 milliarcsecond, which allowed accurate distances out to roughly 1,000 light-years, encompassing perhaps 100,000 nearby stars. Its successor, the Gaia spacecraft, launched in 2013, pushed that limit dramatically further, measuring parallaxes for nearly 2 billion stars with unprecedented accuracy. For the nearest and brightest stars, Gaia can measure distances out to tens of thousands of light-years. But even Gaia cannot reach the nearest galaxies. The Andromeda Galaxy is 2.5 million light-years away. The parallax angle for a star in Andromeda is so absurdly small that no instrument we have ever built, or are likely to build in the foreseeable future, can detect it. We are dealing with angles smaller than 1/1,000,000th of an arcsecond, far below the noise floor of any current technology. So parallax gives us the first rung of what astronomers call the cosmic distance ladder. Think of it as a real ladder, propped against the wall of the unknown. The lowest rung, the most secure rung, is parallax. It is rooted in pure geometry. in the simple, elegant mathematics of triangles. No assumptions about physics are required, no models of stellar behavior, just angles and arithmetic. But this rung only reaches so far. To climb higher, to reach the galaxies and beyond, you need more rungs. And each new rung introduces new assumptions, new uncertainties, and new opportunities for error. This is worth pausing on, because the metaphor of a ladder is more apt than it might first appear. On a real ladder, every rung supports the ones above it. If a lower rung breaks, everything above it collapses. The cosmic distance ladder works the same way. Each method of distance measurement is calibrated against the method below it. Parallax calibrates the nearest Cepheids. Cepheids calibrate the next set of distance indicators. Those indicators calibrate the next. If any rung is flawed, everything above it tilts. And the tilt does not diminish as you climb higher. It propagates. A 5% error at the base becomes a 5% error at the top, affecting distance estimates for galaxies billions of light years away. This cascading vulnerability is what makes the cosmic distance ladder both the most powerful and the most fragile construct in all of observational astronomy. It is the scaffold on which our entire understanding of the size, age, and expansion rate of the universe is built. And the scaffold, as we will see, has wobbled more than once. The next rung up the ladder relies on a different concept entirely. Instead of geometry, it uses physics. Specifically, it uses the physics of light and brightness. To understand how this works, imagine standing in a dark field at night. In the distance, you see a light. You want to know how far away it is. If you know nothing about the light, nothing about its intrinsic nature, you are stuck. It could be a candle 10 meters away. It could be a searchlight 10 kilometers away. Both could appear equally bright from where you stand. The apparent brightness of a light source alone tells you nothing about its distance. But now imagine you know, somehow, that the light is a standard 60-watt incandescent bulb. You know exactly how much light a 60-watt bulb emits. If you can then measure how bright it appears to you, you can calculate the distance. The mathematic is straightforward. The apparent brightness of a light source decreases with the square of the distance. A bulb twice as far away appears 4 times dimmer. A bulb 10 times farther appears 100 times dimmer. A bulb 100 times farther appears 10,000 times dimmer. This is called the inverse square law, and it holds for any source of light, from a candle flame to a supergiant star. This is the concept behind what astronomers call a standard candle. A standard candle is any astronomical object whose intrinsic brightness, its absolute luminosity, is known or can be determined independently. If you know how luminous it truly is, and you measure how luminous it appears from Earth, the inverse square law gives you the distance. The challenge, of course, is finding objects in space that qualify. You need something whose true brightness you can determine without already knowing it's the distance. Something bright enough to be seen across millions of light years, and something common enough to be found in many different parts of the universe. This is where Delta Cephei enters the story. This is where a young man named John Goodricke, observing from a garden in York, England, set in motion a chain of events that would give humanity its most powerful tool for measuring the cosmos. John Goodricke was born on September 17th, 1764, in Groningen in the Dutch Republic. When he was very young, a severe illness, most likely scarlet fever, left him profoundly deaf. He could not hear spoken words. He could not hear music. He could not hear the wind or the birds or the sounds of the city around him. He communicated through writing and lip reading. In an era when deaf individuals were routinely excluded from intellectual life, often assumed to be incapable of learning, Goodricke received an unusually good education. He attended the Braidwood Academy in Edinburgh, one of the first schools for the deaf in Britain, and then studied at the Warrington Academy in England, a progressive institution known for its natural philosophy curriculum. Goodricke was, by all accounts, exceptionally brilliant. At the age of 17, he began observing the star Algol in the constellation Perseus. Algol had been noted as a variable star for centuries, its Arabic name, which roughly translates to the demon's head, hinting at its reputation as an unpredictable, ominous light. But no one had systematically studied its variability. Goodricke did. He observed Algol night after night, recording its brightness with care, and he discovered that its brightness dipped at regular intervals, roughly every 2 days and 20 hours. He proposed, correctly, that Algol was not a single star but a binary system, two stars orbiting each other, with the dimmer star periodically passing in front of the brighter one, eclipsing it, and reducing the total light we see. This was a revolutionary idea for its time. Goodricke presented his findings to the Royal Society of London, and in 1783, at the age of just 19, he was awarded the Copley Medal, one of the highest honours in British science. The medal had previously gone to luminaries like Benjamin Franklin and James Cook, and now it went to a teenage astronomer who could not hear the applause. But Goodricke was not finished. In 1784, he turned his attention to another star, one in the constellation Cepheus. This star was Delta Cephei, and what he found was different from Algol. Delta Cephei was not being eclipsed by a companion. Its brightness changes were intrinsic. The star itself was pulsating, swelling and contracting, growing brighter as it expanded and dimmer as it shrank. The cycle repeated with extraordinary regularity every 5 days, 8 hours, and roughly 47 minutes. It was as steady as any mechanical clock. Goodricke reported his discovery to the Royal Society. The astronomical community took note. And then, in 1786, at the age of 21, John Goodricke died. The cause is believed to have been pneumonia, likely contracted during the long, cold nights he spent observing the stars from exposed locations. He never married. He left behind no children. He never knew what his discovery would become. He never knew that the pulsating star he had catalogued in the constellation Cepheus would give humanity the most powerful distance-measuring tool in the history of astronomy. To appreciate what was at stake, consider what astronomers did not know in Goodricke's era. They did not know how big the Milky Way was. They did not know whether the faint, fuzzy patches of light, called nebulae, visible through telescopes, were clouds of gas within our galaxy or entire galaxies in their own right, lying millions of light-years beyond our borders. They did not know whether the universe was finite or infinite, static or dynamic, young or ancient. They did not know whether other solar systems existed, or whether the Sun was a typical star or a rare exception. These were not minor questions. They were the deepest questions anyone had ever asked about the nature of reality, and the answer to many of them would eventually hinge on a flickering star that a deaf teenager had noticed from a garden in northern England. If you shrink the entire Milky Way down to the size of a standard dinner plate, roughly 25 centimeters across, the solar system would be a speck of dust smaller than a grain of pollen, located about 2/3 of the way from the center to the edge. On that same scale, the Andromeda galaxy would be another dinner about 6 meters away. The nearest large galaxy cluster, the Virgo cluster, would be a collection of dozens of plates scattered roughly 60 meters away, and the observable universe, at that scale, would stretch roughly 23 kilometers in every direction. Everything we know about the distances to those far-flung dinner plates, everything we know about the size and structure of the cosmos beyond our own galaxy, traces back, in one way or another, to the kind of star that John Goodricke found, a Cepheid variable, a star that breathes. But the full power of Cepheid variables would not be unlocked for more than a century after Goodricke's death. It would take another extraordinary mind to find the hidden pattern lurking inside the pulsation. And that mind belonged to a woman whose contributions were, for decades, nearly invisible to history. But what scientists discovered next was worse than anyone expected. Not worse in the sense of tragedy, but worse in the sense of scale. The pattern that emerged from the flickering of Cepheid stars did not just reveal the distances to nearby objects. It revealed that the universe was far larger, far older, and far stranger than anyone had dared to imagine. Henrietta Swan Leavitt was born on July 4, 1868, in Lancaster, Massachusetts. Her father was a congregational minister. She grew up in a quiet, bookish household and attended Oberlin College for 2 years before transferring to what would later become Radcliffe College, the women's counterpart to Harvard University. During her final year of study, she took a course in astronomy, and something about the subject seized her imagination. the precision of it, the vastness of it, the idea that you could point a telescope at the sky and learn something true about objects unimaginably far away. After graduating in 1892, Leavitt travelled, fell ill with a disease that gradually destroyed her hearing, and then, in 1895, she volunteered to work at the Harvard College Observatory. In 1902, she was hired as a permanent staff member, but the word hired requires a caveat. Her position was menial, her pay was minimal, and her role, though intellectually demanding, was defined by rigid boundaries that she was not permitted to cross. Leavitt was one of the so-called Harvard computers, a group of women employed by the observatory to perform the tedious, painstaking labor of analyzing photographic plates. These plates were glass negatives, each one a snapshot of a portion of the sky exposed through the observatory's telescopes over the course of hours, or sometimes entire nights. Each plate contained the images of thousands of stars, pinpricks of silver halide darkened by starlight. The women's job was to catalogue the brightness, position, and spectral characteristics of every star on every plate. They worked in a cramped room on the second floor of the observatory building, hunched over magnifying glasses and comparison standards, measuring, recording, and classifying, hour after hour, day after day. The pay was between 25 and 50 cents per hour, less than what a factory worker earned. The women were not allowed to operate the telescopes themselves. They were generally not credited as primary authors on publications. Their director, Edward Charles Pickering, was by the standards of his time a progressive figure who recognized the intelligence and reliability of his female staff. But he also perpetuated a system in which women did the hardest analytical work while men took the credit and made the decisions. The group was sometimes referred to, even in polite company, as Pickering's harem, a phrase that tells you nearly everything you need to know about the era. Leavitt's specific assignment was to study variable stars in the Magellanic Clouds. The Small Magellanic Cloud and the Large Magellanic Cloud are two irregular galaxies visible from the southern hemisphere, though, in Leavitt's time, they were not known to be separate galaxies. They appeared as hazy, luminous patches in the southern sky, and photographic plates taken from Harvard's observing station in Arequipa, Peru, captured thousands of individual stars within them. Leavitt was looking for variables, stars whose brightness changed over time. She was phenomenally good at this work. It required patience, sharp eyes, and an almost obsessive attention to detail. You had to compare the same star across dozens of plates taken on different nights, noting whether its image was slightly larger or smaller, slightly brighter or dimmer, relative to the comparison stars around it. Over the course of several years, Leavitt identified 1,777 variable stars in the Magellanic Clouds. It was an astonishing feat of observational endurance. Among the variables she catalogued were Cepheid variables, stars that pulsated in the same rhythmic manner as Delta Cephei, brightening and dimming over regular periods. And then, in 1908, Leavitt noticed something that would change the course of science. When she sorted the Cepheids in the Small Magellanic Cloud by their pulsation period, a pattern emerged with startling clarity. The Cepheids that took longer to complete one cycle of pulsation were brighter. The ones with shorter periods were dimmer. This was not a vague correlation, not a fuzzy trend that might or might not be real. It was a tight, clean relationship. If you plotted pulsation period against apparent brightness on a graph, the data points fell along a smooth, well-defined curve. The longer the period, the brighter the star, without exception. This observation contained a hidden insight of staggering importance. The key was the location of the stars. All the Cepheids in the Small Magellanic Cloud were at approximately the same distance from Earth. The Small Magellanic Cloud is about 200,000 light-years away, and the variations in distance among the Cepheids within it are tiny compared to that total distance. This meant that any differences in apparent brightness between Cepheids in the cloud reflected real differences in their intrinsic luminosity. A Cepheid that appeared brighter was not just closer, it was genuinely more luminous, it was putting out more light. And since the pulsation period correlated with apparent brightness, and apparent brightness in this case reflected true luminosity, the pulsation period was directly linked to the star's intrinsic brightness. If you knew how long a Cepheid took to complete one pulsation cycle, you knew, at least in relative terms, how luminous it truly was. Brighter Cepheids pulsate more slowly, dimmer Cepheids pulsate faster. The relationship was consistent across every Cepheid Leavitt examined. She published a preliminary note in 1908 mentioning the trend. Then, in 1912, she published a more detailed analysis based on 25 Cepheids in the Small Magellanic Cloud. The paper was formally authored by Pickering, though Leavitt had done essentially all of the work. In it she wrote, with characteristic understatement, that a remarkable relation between the brightness of these variables and the length of their periods had been found. It was one of the most understated descriptions of a transformative discovery in the history of science. Here is why the period-luminosity relationship, now often called the Leavitt law, matters so profoundly. Recall the concept of the standard candle. If you know how intrinsically bright an object is, and you can measure how bright it appears from Earth, the inverse square law gives you the distance. Cepheid variables are standard candles of extraordinary power. You find a Cepheid anywhere in the sky, in any galaxy, at any distance. You measure how long it takes to complete one pulsation cycle. That period tells you its true luminosity. You then compare that true luminosity to the star's apparent brightness as observed from Earth. The difference between how bright it truly is and how bright it appears gives you the distance. It is a clean, elegant, repeatable method, and it works across millions of light years. Suddenly, astronomers had a way to measure distances far beyond the reach of parallax. They could reach into the depths of the universe, find a pulsating Cepheid, time its heartbeat, and calculate how far away it was. The cosmic distance ladder had gained a transformative new rung, one that extended not just thousands but millions of light years into the void. But here is the problem. Leavitt had established a relative relationship, not an absolute one. She had shown that period and luminosity were correlated, but she had not pinned down the relationship in absolute terms. She knew that a Cepheid with a 10-day period was brighter than one with a 3-day period, but she did not know, in absolute units of luminosity, exactly how bright either one was. To use Cepheids as distance markers in the real universe, someone needed to determine the actual, absolute luminosity of at least one Cepheid. This required knowing the distance to at least one Cepheid by some independent method, like parallax, and then using that known distance combined with the star's apparent brightness to calculate the true luminosity. Once you had that anchor point, you could calibrate the entire period-luminosity relationship. This calibration problem sounds simple, but it would plague Cepheid-based distance measurements for the next century. The nearby Cepheids, whose distances could be measured by parallax, were few in number and had significant uncertainties in their parallax values. And the errors introduced by small miscalibrations were not small. They were catastrophic. A 10% error in the calibration translated directly into a 10% error in every distance measured using Cepheids, which in turn translated into errors in the estimated size, age, and expansion rate of the universe. We will return to this calibration problem in detail, because it led to some of the most spectacular blunders in the history of astronomy. But first, let us understand the physics behind the pulsation itself. What is happening inside a Cepheid variable that makes it swell and shrink with such clockwork regularity? The answer lies in the physics of stellar interiors, in the way energy flows through the layered structure of a massive star, and how that flow can become unstable under specific conditions. In a normal, stable star like our Sun, energy generated by nuclear fusion in the core, primarily the conversion of hydrogen into helium, radiates outward through the star's layers. The star exists in a state of hydrostatic equilibrium. Gravity pulls inward, trying to collapse the star. Radiation pressure and gas pressure push outward, resisting the collapse. These forces balance. The star holds steady, its size and brightness remaining approximately constant over long stretches of time. Our Sun has been in this equilibrium for about 4.6 billion years and will remain so for roughly another 5 billion. But in a Cepheid variable, this equilibrium breaks down in a specific layer of the star. The layer in question is one where helium is undergoing a particular kind of ionization. In this zone, Helium atoms are being stripped of their second electron, transitioning from singly ionized helium, which has lost one of its two electrons, to doubly ionized helium, which has lost both. This transition has a remarkable property. When the layer is compressed, it becomes more opaque to radiation. It absorbs more light, it traps more energy. This trapped energy heats the layer, increases the pressure within it, and drives the layer to expand outward. But as the layer expands, something changes. It becomes less opaque. It becomes more transparent. Radiation can now escape through it more easily. The layer cools. The pressure drops, and gravity, patient and relentless, pulls the layer back inward. The compression begins again. The opacity increases. Energy is trapped once more. The cycle repeats. This mechanism is called the kappa mechanism, named after the Greek letter kappa, which represents opacity in the equations of stellar structure. It is, in essence, a heat engine operating inside the star. The helium ionization zone acts like a valve, rhythmically trapping and releasing energy. The star pulsates because energy is being cyclically stored and released in this one critical layer. The period of the pulsation, how long each cycle takes, depends on the physical properties of the star, primarily its size, its mass, and its average density. Larger, more luminous Cepheids have longer periods because the pulsation wave takes longer to travel through them. This is why the period-luminosity relationship exists. It is not a coincidence. It is a direct consequence of the physics of stellar pulsation. The physics is elegant, beautiful even, but it also reveals something important about Cepheids that is easy to overlook. Not every star pulsates. The kappa mechanism only works in stars that occupy a specific region of what astronomers call the Hertzsprung-Russell diagram, a plot that maps stars according to their temperature and luminosity. This region is called the instability strip, a narrow diagonal band that cuts across the diagram from the bright, cool upper right to the fainter, hotter lower left. Stars passing through the instability strip during their evolution develop the right combination of temperature and luminosity for the helium ionization zone to drive sustained pulsation. Stars outside the strip are too hot or too cool for the mechanism to operate. Their helium ionization zones sit at the wrong depth, and any perturbations damp out rather than amplify. What this means is that Cepheid pulsation is not a permanent condition. It is a phase. A star does not become a Cepheid at birth and remain one until death. Instead, a star crosses the instability strip during its post-main sequence evolution, as it moves from the blue side of the diagram to the red side, or sometimes crosses back again. Delta Cephei itself is in this transient phase right now, a massive star in a temporary state of rhythmic instability. In 10 or 20 million years, it will have evolved beyond the strip, and its pulsation will cease. The heartbeat will stop. But for now, for this cosmological instant, the physics is right, the conditions are met, and the star breathes. But the kappa mechanism also introduces complications. The kappa mechanisms depends on the chemical composition of the star, particularly its metallicity. In astronomy, metallicity refers to the abundance of elements heavier than hydrogen and helium. Stars with higher metallicity have more heavy elements in their interiors, which can affect the opacity of the helium ionization zone and alter the pulsation properties. This means the period-luminosity relationship is not perfectly universal. It can shift slightly depending on the chemical makeup of the Cepheids being studied. Cepheids in metal-rich environments may behave slightly differently from Cepheids in metal-poor environments. To put this in perspective, consider the difference between Cepheids in our own galaxy and those in the Small Magellanic Cloud, where Leavitt discovered the period-luminosity relationship. The Milky Way is a large metal-rich galaxy. Its interstellar medium has been enriched by billions of years of stellar nucleosynthesis, the process by which stars forge heavier elements in their cores and scatter them into space when they die. The Small Magellanic Cloud, by contrast, is a small metal-poor dwarf galaxy with a much less enriched interstellar medium. If metallicity affects the period-luminosity relationship, then the relationship calibrated in the Milky Way might be slightly different from the one that applies in the Magellanic Clouds, which might be different again from the one that applies in a massive elliptical galaxy with a completely different chemical history. The size of this effect has been debated for decades, and the debate is not settled. Some theoretical models predict a significant dependence on the order of a few tenths of a magnitude per dex of metallicity difference. Observational studies have produced conflicting results. Some find the predicted effect, others do not. The disagreement persists, and it feeds directly into the uncertainty of the cosmic distance scale. And it gets worse. There is not just one kind of Cepheid variable. There are at least two major types, and confusing them led to one of the greatest errors in the history of cosmology. The first type is called a classical Cepheid, or a type 1 Cepheid. These are young, massive luminous, supergiant stars, typically 5 to 20 times the mass of our Sun. They are found in the spiral arms and disks of galaxies, in regions where star formation is active and ongoing. Delta Cephei itself is a classical Cepheid. These are the stars that Leavitt studied in the Magellanic Clouds, and they obey a specific, well-defined period-luminosity relationship. The second type is called a type 2 Cepheid, sometimes referred to as a W Virginius star, after the prototype star W Virginius. Type 2 Cepheids are older, less massive, and significantly less luminous than their classical counterparts. They are found in the halos and globular clusters of galaxies, in regions populated by ancient metal-poor stars. Critically, and this is the point that would cause decades of confusion, type 2 Cepheids follow a different period-luminosity relationship. For the same pulsation period, a type 2 Cepheid is substantially dimmer than a classical Cepheid, by roughly 1.5 magnitudes on average. In terms of actual luminosity, this means a classical Cepheid is roughly 4 times brighter than a type 2 Cepheid with the same period. Now, imagine what happens if you mistake one type for the other. If you observe a Cepheid in a distant galaxy and assume it is a classical Cepheid when it is actually a type 2 Cepheid, you will overestimate its intrinsic brightness. You will think it is more luminous than it really is. When you compare that inflated luminosity to the star's apparent brightness, the inverse square law will spit out a distance that is too small. The galaxy will appear closer than it actually is. And if you use that incorrect distance as the foundation for other measurements, the error cascades outward, infecting every subsequent calculation that depends on it. This is exactly what happened in the early 20th century, and it led to a crisis that shook the foundations of astronomy. In the early 1920s, a fierce and public debate was raging in the astronomical community. It is known to history as the Great Debate, and it centered on a single question of profound importance. Were the spiral nebulae, those beautiful pinwheel-shaped smudges of light visible through large telescopes, structures within our own Milky Way galaxy, or were they separate galaxies in their own right, island universes lying at vast distances beyond the borders of our own? The stakes could not have been higher. If the spiral nebulae were internal features of the Milky Way, then our galaxy was essentially the entire universe. Everything that existed was contained within it. But if the spiral nebulae were external galaxies, then the universe was almost inconceivably larger than anyone had imagined. A vast expanse populated by billions of separate stellar systems, each one comparable in size to the Milky Way itself. On one side of the debate stood Harlow Shapley, an ambitious and charismatic astronomer who had used Cepheid variables to estimate the size of the Milky Way. Shapley had studied Cepheids in globular clusters and concluded that the Milky Way was enormous, perhaps 300,000 light-years across, far larger than previous estimates. He argued that the spiral nebulae were relatively nearby features within this vast galaxy. On the other side stood Heber Curtis, an astronomer at the Lick Observatory in California. Curtis believed the Milky Way was much smaller, perhaps 30,000 light-years across, and that the spiral nebulae were separate galaxies at immense distances. He pointed to evidence such as the novae observed in spiral nebulae, which appeared much dimmer than novae in the Milky Way, suggesting enormous distances. The formal debate took place on April 26, 1920, at the Smithsonian Museum of Natural History in Washington, D.C. It was attended by the leading astronomers of the day. Neither side won decisively. The data was insufficient. The evidence was ambiguous. Both men made strong arguments, and both had weaknesses in their positions. The question remained stubbornly open. What made the great debate so extraordinary was not merely the scientific stakes, but the philosophical ones. The question of whether the spiral nebulae were separate galaxies was, at its root, a question about humanity's place in the cosmos. If Shapley was right, the universe was large but comprehensible, a single vast galaxy in which we occupied a known, if peripheral, position. If Curtis was right, the universe was a wilderness of galaxies, stretching beyond counting, and our entire Milky Way was just one island among countless millions. The audience in the Smithsonian that evening understood this. They were not just listening to a technical dispute about photographic plates and angular measurements. They were listening to two competing visions of reality, two possible universes, and they had no way to determine which one they actually lived in. The instruments of the day could not settle the matter. The answer would require a bigger telescope, a different kind of star, and a young astronomer with the ambition youth to muse both. And then Edwin Hubble stepped into the story. Hubble was working at the Mount Wilson Observatory in the mountains above Pasadena, California. At his disposal was the 100-inch Hooker telescope, the largest telescope in the world at the time, with a mirror 2.5 meters in diameter that could gather light from extraordinarily faint and distant objects. Hubble was methodical, ambitious, and driven. He was also, by many accounts, not particularly generous about acknowledging the work of others. In 1923, Hubble turned the Hooker telescope toward the Andromeda Nebula, the largest and brightest of the spiral nebulae. He was searching for novae, stars that brightened suddenly and dramatically. On the night of October 5th, 1923, he took a photographic plate of Andromeda that captured what he initially marked as a nova, labeling it with the letter N. But as he gathered more plates over the following weeks, he realized the star was not a nova. It was not brightening and fading in the irregular, explosive manner of a nova. It was pulsating rhythmically. It was a Cepheid variable. Hubble crossed out the N he had written on the plate and wrote, in his own hand, "Var," with an exclamation mark. That plate, with its crossed-out N and its jubilant exclamation, still exists. It is preserved in the archives of the Carnegie Observatories. It may be the most important photographic plate in the history of astronomy. Using Leavitt's period-luminosity relationship, Hubble calculated the distance to the Cepheid in Andromeda, and therefore to the Andromeda Nebula itself. His answer was approximately 900,000 light-years. This was far beyond the most generous estimates of the Milky Way's diameter. The Andromeda Nebula could not possibly be inside our galaxy. It was a separate galaxy, an island universe. The great debate was settled. When Hubble's results were formally announced at a meeting of the American Astronomical Society on January 1st, 1925, the reaction was immediate and decisive. The universe had just grown enormously. The Milky Way, which had seemed like the entire cosmos, was suddenly just one galaxy among what turned out to be millions, then billions, then trillions. The philosophical implications were staggering. But here is what makes this truly terrifying. Hubble's distance to Andromeda was wrong, not subtly wrong, not within the margins of reasonable uncertainty. It was wrong by a factor of nearly 3. He had calculated 900,000 light-years. The true distance, as measured by modern instruments, is approximately 2.5 million light-years. His estimate put Andromeda less than half as far away as it actually is, and the error was not caused by sloppy work or a flawed telescope. The error was embedded in the calibration of the Cepheid period-luminosity relationship itself, a calibration that had unknowingly mixed together two different types of Cepheid stars. The correction would not come for another 3 decades, and when it did come, it would double the size of the known universe overnight. The scale of the error deserves emphasis. Hubble believed the Andromeda galaxy was less than 1 million light-years away. In reality, it is roughly 2.5 times farther. This is not a subtle miscalculation. If you told someone that a city was 300 kilometers away, and it turned out to be 750 kilometers away, they would miss it by a wide margin. In the context of galactic distances, an error of this magnitude had cascading consequences. It meant that every galaxy beyond Andromeda was also farther away than calculated. It meant that the universe was correspondingly larger. It meant that the expansion rate was correspondingly slower, and it meant that the age of the universe inferred from the expansion rate was correspondingly greater. With Hubble's original calibration, the universe appeared to be roughly 1.8 billion years old. This was a deeply troubling number because geologists had already established, through radioactive dating of rocks, that the Earth itself was at least 3.3 billion years old. The planet was apparently older than the universe that contained it. This contradiction, known as the age paradox, was one of the most embarrassing problems in 20th century science. It cast doubt not just on the Cepheid distance scale, but on the entire framework of the expanding universe. The resolution would come from an unexpected direction, not from a better telescope or a better mathematical technique, but from a careful look at the different kinds of stars in a galaxy 2.5 million light-years away, and it would require a war. The story of how astronomers struggled to calibrate the Cepheid distance scale is one of the most dramatic and instructive chapters in the history of science. It is a story of brilliant minds grappling with subtle errors, of assumptions that seemed perfectly reasonable but turned out to be catastrophically wrong, and of a universe that stubbornly refused to conform to the models that humans built for it. To understand how we arrived at our current state of knowledge and our current state of confusion, we need to trace the long, winding path of calibration attempts, each one revealing a new layer of complexity, each one pushing the answer a little further from where anyone expected it to be. The first serious attempt at calibrating the period-luminosity relationship came almost immediately after Leavitt published her results. In 1913, just a year after her landmark paper, the Danish astronomer Ejnar Hertzsprung tried to anchor the relationship in absolute terms. He needed the distance to at least one Cepheid variable, measured by a method independent of the period-luminosity relationship itself. Direct parallax measurements for Cepheids were not available at the time, as even the nearest Cepheids were too far away for the ground-based parallax techniques of the early 20th century. So Hertzsprung used a statistical method called secular parallax, which exploits the motion of the Sun through the galaxy to create a larger effective baseline for distance measurements. By analyzing the average motion of a group of Cepheids, rather than the parallax of any single star, Hertzsprung could estimate an average distance for the group. His calibration was reasonable for its time, but the uncertainties were large. The sample of Cepheids with measured proper motions was small, and the statistical method introduced significant scatter. Hertzsprung derived a distance to the small Magellanic Cloud of roughly 30,000 light-years, which was far too small. The modern value is about 200,000 light-years, but his work established the basic approach. You calibrate the 0 point of the period-luminosity relationship using nearby stars with independently known distances, and then apply the calibrated relationship to more distant stars. Harlow Shapley took this approach further in the late 19-teens. He calibrated the Cepheid relationship using statistical parallaxes, and then used it to estimate the distances to globular clusters, dense spherical aggregations of old stars that orbit the Milky Way. Shapley's results were transformative. He found that the globular clusters were distributed in a vast, roughly spherical halo centered not on the Sun but on a point tens of thousands of light-years away, in the direction of the constellation Sagittarius. This led him to the correct conclusion that the Sun was not at the center of the Milky Way, but rather located far out in the disk. His estimate of the Milky Way's diameter was about 300,000 light-years, which turned out to be roughly 3 times too large. But the basic picture, a vast galaxy with the Sun in the outskirts, was correct. The critical problem lurking beneath both Hertzsprung's and Shapley's work was that they were calibrating the relationship without distinguishing between different types of Cepheids. No one at the time realized that there were 2 distinct populations, classical Cepheids and type 2 Cepheids, each obeying a different period-luminosity relationship. The calibration samples included a mix of both types, which blurred the relationship and introduced systematic errors. The confusion would not be resolved until the early 1950s, when the German-born American astronomer Walter Baade made a discovery that would rewrite the distance scale of the entire universe. Bardi was a quiet, meticulous observer who worked at the Mount Wilson Observatory. During World War II, the wartime blackout regulations in Los Angeles had dramatically reduced the light pollution that normally plagued the observatory, and Bade took full advantage of the unusually dark skies. While the city below sat in enforced darkness, its street lights extinguished, its neon signs dark, its coastline blacked out against the threat of Japanese submarine attack, Bade had the mountain practically to himself. Many of the observatory's American-born astronomers had been called away to war-related work, leaving the telescopes available for extended observing runs. Bardi, a German citizen classified as an enemy alien despite his long residence in the United States, was restricted in his movements but free to observe. The irony was exquisite. A war that had darkened a continent gave one astronomer the darkness he needed to see farther than anyone had seen before. He turned the 100-inch Hooker telescope, the same test Hubble had used to discover Cepheids in Andromeda, toward the Andromeda galaxy and took long-exposure photographs of unprecedented depth and clarity. What Bardi saw puzzled him. He was able to resolve individual stars in the central bulge of Andromeda for the first time, and those stars were different from the ones in the galaxy's spiral arms. The disk and spiral arms contained young, hot blue stars, stars that Bade called Population 1. The central bulge contained older, cooler, redder stars, Population 2. This distinction in stellar populations turned out to be fundamental. Population 1 stars are metal-rich, younger, and found in the disks of spiral galaxies, where star formation continues. Population 2 stars are metal-poor, older, and found in galactic halos and globular clusters. Bade realized that the Cepheid variables found in these two populations were different types with different properties. The classical Cepheids of Population 1, like Delta Cephei, were bright, young supergiants. The Type 2 Cepheids of Population 2, like W. Virginis, were older, less massive, and significantly less luminous. For the same pulsation period, a classical Cepheid was roughly 4 times brighter than a Type 2 Cepheid. The implications were shattering. Hubble had observed classical Cepheids in the Andromeda galaxy, but had calibrated his distance scale using a mixture that included Type 2 Cepheids from globular clusters. Because Type 2 Cepheids are fainter for the same period, the mixed calibration underestimated the true brightness of the classical Cepheids Hubble had observed. This meant the classical Cepheids were actually brighter than Hubble assumed, which meant they had to be farther away than he calculated. In 1952, at a meeting of the International Astronomical Union in Rome, Bade stood before the assembled astronomers of the world and announced his findings. All extragalactic distances, he declared, needed to be roughly doubled. The universe had just gotten twice as big overnight. The age of the universe, which had been embarrassingly young based on Hubble's original distance scale, suddenly became more reasonable. The numbers are striking. Before Bade's correction, Hubble's distances implied a universe roughly 1.8 billion years old. This was acutely embarrassing, because geologists had already determined that the Earth itself was at least 3.3 billion years old. The universe appeared to be younger than one of the rocks sitting on its surface. After Bade's correction, the universe's age jumped to roughly 3.6 billion years, which was still young by modern standards, but at least no longer younger than the Earth. The paradox, while not fully resolved, was significantly softened. Let that sink in. A single correction to the Cepheid calibration, motivated by the realization that two types of variable stars had been confused, doubled the known size of the universe and alleviated one of the most embarrassing contradictions in all of science. The entire map of the cosmos was redrawn because someone looked more carefully at the difference between young stars and old stars in a galaxy 2.5 million light-years away. But the calibration problems did not end with Bade. They continued through the 20th century and, in many ways, they persist to this day. Let us examine the major sources of uncertainty that have bedeviled Cepheid distance measurements, the different angles from which astronomers have attacked the problem, and why the debate is still not resolved. The first persistent challenge is interstellar extinction. The space between stars is not empty. It is laced with thin curtains of gas and dust. remnants of dead stars, and the raw material for new ones. This interstellar dust absorbs and scatters starlight, particularly at shorter wavelengths. The effect is twofold. Stars appear dimmer than they should be, and they appear redder, because blue light is scattered away more efficiently than red light. If you do not correct for this dimming and reddening, you will overestimate the distance to any star you observe. You will think it is farther away because it appears fainter. The difficulty is that interstellar extinction is not uniform. It is patchy, clumpy, and unpredictable. Some lines of sight through the galaxy pass through dense clouds of dust where extinction is severe. Others pass through relatively clear corridors where extinction is minimal. The amount of extinction along any particular line of sight depends on the distribution of dust clouds between you and the star, and mapping that distribution accurately is one of the great ongoing challenges of observational astronomy. Astronomers estimate extinction by measuring the color excess of stars. Every star has a predictable color based on its spectral type and temperature. If a star appears redder than expected, the excess redness can be attributed to interstellar dust, and the amount of reddening can be used to estimate the total extinction. But this method assumes you know the star's intrinsic color correctly, and for Cepheids, which change color as they pulsate, this introduces additional uncertainty. The corrections are not trivial. They require careful photometry in multiple wavelength bands and rely on models of dust grain properties that are themselves not perfectly known. One approach to reducing the impact of extinction is to observe Cepheids at infrared wavelengths rather than in visible light. Infrared radiation has longer wavelengths and passes through dust much more easily than visible light. A star that is dimmed by 1 magnitude in visible light might be dimmed by only a fraction of a magnitude in the infrared. Beginning in the 1980s, astronomers started conducting systematic infrared surveys of Cepheid variables, and the results were encouraging. The period-luminosity relationship in the infrared was tighter, with less scatter, than the relationship in visible light. This was partly because the extinction correction was smaller, and partly because Cepheids show less variation in brightness at infrared wavelengths over their pulsation cycle. The star's temperature changes, which strongly affect its visible light brightness, have a smaller effect on its infrared brightness. The second major challenge is metallicity, the chemical composition of the Cepheid. As we discussed, the kappa mechanism that drives Cepheid pulsation depends on the opacity of the helium ionization zone, and opacity is influenced by the star's overall metallicity. Stars in different environments, different galaxies, different regions within the same galaxy can have very different metallicities. If the period-luminosity relationship shifts with metallicity, then using a calibration derived from Cepheids in one environment to measure distances in another environment introduces a systematic error. The magnitude of the metallicity effect has been debated intensely for decades. Some studies, using both theoretical models and observational data, find that metal-rich Cepheids are intrinsically brighter than metal-poor Cepheids at the same period. Others find a smaller effect, and a few find no significant effect at all. The disagreement is partly due to the difficulty of measuring metallicity accurately for distant stars, and partly due to the challenge of disentangling metallicity effects from extinction effects, which can mimic each other. A metal-rich Cepheid that is slightly brighter might be confused with a metal-poor Cepheid that has less dust along the line of sight. Separating these effects requires exquisitely precise observations in multiple wavelength bands, combined with detailed spectroscopic analysis, and even then, the answers are not always clear. The third challenge is the geometric calibration of the 0 point, the anchor of the entire period-luminosity relationship. To use Cepheids as absolute distance indicators, you must know the absolute luminosity corresponding to at least one pulsations period. This requires an independent distance measurement, preferably a geometric one like trigonometric parallax, to at least one, and ideally several, Cepheids. For most of the 20th century, such measurements were extremely difficult. The nearest known Cepheids were hundreds of light-years away, too far for accurate ground-based parallax measurements. The Hipparcos satellite, launched in 1989 by the European Space Agency, provided the first space-based trigonometric parallaxes for a small number of Cepheids. The most important was Polaris, the North Star, which is a low-amplitude Cepheid with a pulsation period of about 4 days. Hipparcos measured a parallax for Polaris that implied a distance of roughly 430 light-years. But the uncertainty was large enough to accommodate a range of distances. Other Cepheids measured by Hipparcos had even larger relative uncertainties. The zero-point calibration improved, but it remained one of the weakest links in the chain. The Gaia spacecraft, launched in 2013, represented a quantum leap in parallax precision. Gaia has measured trigonometric parallaxes for nearly 2 billion stars, including several hundred Cepheids in the Milky Way. For the first time, direct geometric distances to a substantial sample of Cepheids became available, allowing a much more robust calibration of the period-luminosity relationship. But even Gaia's measurements are not without controversy. Some Cepheids show evidence of being in binary or multiple star systems, which can contaminate the parallax measurement. Others have been flagged as having potentially unreliable astrometric solutions due to their photometric variability. The very brightness changes that define them as Cepheids can, ironically, interfere with the precise measurement of their positions. A fourth angle of attack on the calibration problem came from a completely different direction, one that bypassed the period-luminosity relationship of Cepheids in the Milky Way, and instead used geometric distances to Cepheids in other galaxies. The technique is called the eclipsing binary method. If you can find a Cepheid variable in a detached eclipsing binary system, a system where two stars orbit each other and periodically eclipse one another, you can determine the physical sizes of both stars from the shape of the eclipse-like curve and their radial velocity curves. Combining the physical size with the angular size, measured by interferometry, gives a direct geometric distance. In 2013, a team led by Grzegorz Pieczynski used this method to measure the distance to the Large Magellanic Cloud with unprecedented precision. They found a distance of approximately 163,000 light-years, with an uncertainty of only about 2%. This was the most accurate distance ever measured to a galaxy beyond the Milky Way, and it provided a powerful anchor for the Cepheid distance scale. But even this measurement has been debated. Different teams, using slightly different methods and different samples of eclipsing binaries, have obtained slightly different distances. The discrepancies are small, a few percent, but at the level of precision required for modern cosmology, a few percent matters enormously. The fifth and perhaps most consequential angle of approach involves a completely different type of standard candle, one that extends far beyond the reach of Cepheids. Type 1a supernovae are thermonuclear explosions that occur in binary star systems when a white dwarf, the dense remnant of a dead star, accumulates enough mass from a companion star to exceed the Chandrasekhar limit, roughly 1.4 solar masses. At that critical mass, the white dwarf collapses and detonates in a colossal explosion, briefly shining with the luminosity of several billion suns. Because the explosion is triggered at a specific mass threshold, all Type 1a supernovae reach approximately the same peak luminosity, making them excellent standard candles for cosmological distances. The power of Type 1a supernovae is that they can be observed billions of light-years away, far beyond the distance at which individual Cepheids can be resolved. In the late 1990s, two teams using Type 1a supernovae to measure the expansion rate of the universe made one of the most shocking discoveries in the history of cosmology. They found that the expansion of the universe is not slowing down, as everyone had assumed. It is speeding up. Some mysterious force or property of space itself, is pushing the galaxies apart at an ever-increasing rate. This unknown driver was called dark energy, and its discovery earned Saul Perlmutter, Brian Schmidt, and Adam Riess the Nobel Prize in Physics in 2011. But here is the catch that brings us back to our story. To calibrate Type 1a supernovae as standard candles, you first need to know the distance to several galaxies that have hosted Type 1a supernovae, and the most reliable way to measure those distances is with Cepheid variables. you need to find galaxies that contain both Cepheids and Type 1a supernovae. You use the Cepheids to determine the distance to the galaxy. You then use that distance to calculate the absolute luminosity of the supernova. Once calibrated, the supernovae can be used to measure distances to galaxies much farther away, where no individual Cepheids can be resolved. The entire structure rests on the Cepheids. They are the foundation. If the Cepheid distances are off by even a small amount, the supernova calibration is off by the same amount, and every distance measurement based on supernovae is off as well. The error does not cancel out, it compounds. A 5% error in the Cepheid 0 point becomes a 5% error in the Hubble constant, the number that describes the expansion rate of the universe, and a 5% error in the Hubble constant translates into a 5% error in the estimated age of the universe, roughly 700 million years. 700 million years is almost as long as the entire period during which multicellular life has existed on Earth. That is the margin of error we are discussing. Something is wrong with our assumptions. Or, more precisely, something might be wrong, and the disagreement over what exactly is wrong has become one of the most contentious and consequential debates in modern physics. It is called the Hubble tension. The Hubble tension is the persistent, statistically significant discrepancy between two independent measurements of the Hubble constant. One measurement comes from the local distance ladder, the chain of Cepheids and Type 1a supernovae that we have been describing. This method, refined over decades by teams led by Adam Riess at Johns Hopkins University and the Space Telescope Science Institute, gives a Hubble constant of approximately 73 kilometers per second per megaparsec. A megaparsec is about 3.26 million light-years, so this number means that for every 3.26 million light-years of distance between us and a galaxy, that galaxy is receding from us at an additional 73 kilometers per second. The other measurement comes from the cosmic microwave background, the faint glow of radiation left over from the Big Bang. This radiation, detected by the Planck satellite with extraordinary precision, carries an imprint of the conditions of the universe when it was only 380,000 years old. By analyzing the statistical patterns in this radiation, cosmologists can infer the properties of the universe, including its expansion rate, using the standard cosmological model known as lambda CDM. This method gives a Hubble constant of approximately 67.4 kilometers per second per megaparsec. The difference between 73 and 67.4 is about 8%. That might not sound like much, but both measurements claim very high precision, with uncertainties of only about 1 to 2%. The two values are separated by roughly 4 to 5 sigma, a statistical measure meaning that the probability of the discrepancy being due to random chance is less than 1 in 10,000. In particle physics, a 5 sigma result is considered a discovery. In cosmology, a 4 to 5 sigma tension between two fundamental measurements of the same quantity is a crisis, and Delta Cephei's legacy sits right at the heart of it. To appreciate the weight of this tension, consider what is really being debated. It is not just a number. The Hubble constant determines the rate of cosmic expansion, and from that rate, you can work backward to determine when the expansion began, which gives you the age of the universe. A Hubble constant of 73 implies an age of roughly 12.9 billion years. A Hubble constant of 67.4 implies an age of roughly 13.8 billion years. The difference is about 900 million years. 900 million years is not an abstraction. It is a span of time with tangible meaning. 900 million years ago on Earth, the first complex multicellular organisms were just beginning to appear in the oceans. The entire Cambrian explosion, the sudden diversification of animal life that produced most of the major body plans we see today, lay hundreds of millions of years in the future. The difference between 12.9 and 13.8 billion years is not a rounding error. It is the difference between a universe that is comfortably old enough to accommodate its oldest objects and one that might be uncomfortably young. The James Webb Space Telescope has observed galaxies that appear to have formed within the first few hundred million years after the Big Bang galaxies that seem surprisingly massive and mature for their age. If the universe is only 12.9 billion years old, these early galaxies had even less time to form than we thought. The puzzle of how they grew so quickly becomes even more acute. Every fraction of a billion years matters. And all of this question of cosmic age and the formation of the earliest galaxies, traces back to the calibration of pulsating stars in nearby galaxies. The precision that cosmology demands is extraordinary, and the vulnerability of the entire enterprise to small, systematic errors in that calibration is sobering. If the Cepheid calibration is slightly off, if there is a systematic error hiding in the extinction corrections, or the metallicity dependence, or the geometric zero point, that could explain part or all of the discrepancy. Alternatively, if the Planck measurement is affected by some subtle systematic effect in the analysis of the cosmic microwave background data, or if the lambda CDM model is missing a piece of physics, that could explain it too. Or perhaps both sides have small errors that combined account for the tension. Years of meticulous work by multiple independent teams have searched for a smoking gun, a clear, identifiable error that would resolve the tension. The Cepheid distances have been checked and rechecked using different methods. Different teams have used different samples of Cepheids, different extinction correction methods, different metallicity corrections, and different geometric anchors. The result stubbornly refuses to change. The local measurement keeps landing near 73. The cosmic microwave background measurement keeps landing near 67. In 2022, the team led by Rias used the James Webb Space Telescope, with its superior infrared sensitivity and angular resolution, to re-observe Cepheids in several galaxies that had previously been studied with the Hubble Space Telescope. The concern was that the Hubble Space Telescope, in crowded stellar fields, might be blending the light of a Cepheid with the light of nearby unresolved stars, artificially brightening the Cepheid and biasing the distance measurement. The James Webb Space Telescope, with its sharper vision, could separate the Cepheid from its neighbours more cleanly. The result was unambiguous. The James Webb observations confirmed the Hubble Space Telescope measurements. The blending effect was not significant enough to explain the tension. The Cepheid distances were not biased in the way critics had hoped. Other independent methods have been brought to bear on the problem. Tip of the red giant branch stars, or TRGB stars, offer an alternative standard candle that can be calibrated independently of Cepheids. Surface brightness fluctuations in elliptical galaxies provide another distance indicator. Gravitational lensing time delays, where light from a distant quasar is bent and split by an intervening galaxy, can provide a geometric distance measurement that bypasses the Cepheid ladder entirely. Megamaser distances, based on water masers in the accretion disks of distant black holes, offer yet another geometric approach. Some of these alternative methods support the higher Hubble constant value, around 73. Others fall somewhere in between. A few lean toward the lower Planck value. The landscape is complicated, and the resolution is not yet in sight. But through it all, the Cepheid distance ladder remains the primary backbone of the local distance measurement. And Delta Cephei, the humble prototype, the star that started it all, remains the archetype against which all other Cepheids are compared. There is a deeper lesson here about the nature of scientific measurement. Every measurement is a chain of inferences. You measure parallax to get the distance to nearby Cepheids. You use those distances to calibrate the period-luminosity relationship. You apply the calibrated relationship to Cepheids in other galaxies to get those galaxies' distances. You use those distances to calibrate Type 1a supernovae. You use the supernovae to measure distances to the most remote galaxies. You combine those distances with redshift measurements to determine the expansion rate of the universe. Every link in the chain depends on the link before it. Every link introduces assumptions, and every assumption is an opportunity for error. The chain is long, the chain is delicate, and the chain begins with a flicker. Wendy Friedman, one of the most distinguished observational cosmologists of the modern era, has spent decades working on the Cepheid distance scale. She led the Hubble Space Telescope Key project, which in 2001 produced one of the most influential measurements of the Hubble constant finding a value of 72 kilometers per second per megaparsec with an uncertainty of about 8%. More recently, Friedman has championed the use of TRGB stars as an alternative to Cepheids, arguing that they may be less susceptible to certain systematic effects. Her most recent analyses suggest a Hubble constant closer to 70, splitting the difference between the Cepheid-based value and the Planck value, but other teams dispute her TRGB calibration, and the debate continues. The situation is, to put it mildly, unsettled. Some physicists have suggested that the Hubble tension might require entirely new physics to resolve. Perhaps there is a form of early dark energy that was present in the first few 100,000 years after the Big Bang, altering the expansion rate during that critical period, and leaving an imprint in the cosmic microwave background that the standard model does not account for. Perhaps there are additional neutrino species beyond the three that the standard model of particle physics predicts, which would affect the expansion history of the early universe. Perhaps dark energy itself is not constant, as the cosmological constant assumes, but evolves over time, changing its influence on the expansion rate. Each of these proposals has implications far beyond cosmology. They touch on fundamental physics, on the nature of matter and energy, on the behavior of the universe at its earliest moments, and the observational test, the way we distinguish between these possibilities, depends critically on getting the distance scale right, getting the Cepheid calibration right, getting the Hubble constant right. There is a way to think about this that makes the scale of the challenge vivid. If you could somehow lay a ruler from Earth to the most distant galaxy, whose distance has been calibrated using the Cepheid distance ladder, the ruler would stretch roughly 100 million light-years. The Cepheids themselves can only be resolved in galaxies within about 30 to 40 megaparsecs, roughly 100 to 130 million light-years. Beyond that, we rely on supernovae and other techniques that are calibrated through the Cepheids. The furthest Type 1a supernovae used in cosmological measurements are billions of light-years away at redshifts of 1 or more, meaning we are seeing them as they were when the universe was roughly half its current age. If the Cepheid rung of the distance ladder is off by 2%, the error propagates through the supernova calibration and affects distance measurements all the way out to those billions of light-years. 2%. That is the precision we need. And whether we have achieved it remains an open question. At the heart of this enormous, universe-spanning uncertainty sits a small pulsating star in the constellation Cepheus, 890 light-years away, swelling and contracting every 5.37 days. A star that a deaf teenager noticed changing in 1784. A star that a woman at Harvard catalogued and compared to its cousins. A star whose gentle rhythm unlocked the distances to galaxies and forced us to confront the true scale of the cosmos. And this is where the answer becomes deeply unsettling, because the question is no longer just about distance. It is about certainty. It is about how much we really know. We have built our understanding of the age and size and expansion rate of the universe on a chain of reasoning that begins with Cepheid variables, and we are discovering that the chain may have weak links that we have not fully identified. The stakes could not be higher. If the chain holds, our picture of the cosmos is robust. If it does not, everything from the age of the universe to the nature of dark energy may need to be reconsidered. The deeper truth about Delta Cephei and its kin is that they expose a fundamental vulnerability in our understanding of the universe. Not a technical vulnerability, though there are plenty of those. A philosophical vulnerability, an epistemological one. Cepheid variables reveal just how much of what we claim to know about the cosmos depends on a chain of inference that stretches across billions of light-years and is anchored, at its base, by assumptions that we are still testing. Consider what we are asking when we ask how big the universe is. We are asking about regions of space so remote that light from them has been travelling for billions of years to reach us. We are asking about objects so distant that they have been receding from us since before the Earth existed. We are asking about distances so vast that no human, no spacecraft, no probe will ever traverse them. And yet we claim to know these distances to within a few percent. We print them in textbooks. We teach them to children. We use them to calculate the age of the universe, the density of dark matter, the equation of state of dark energy. But every one of those numbers traces back, eventually, through a chain of reasoning, to a handful of pulsating stars whose distances we have measured geometrically. The chain goes from parallax to Cepheids to supernovae to the Hubble flow. Each link is well understood. Each link has been tested and retested, but the chain is long, and the precision required at the end is extraordinary. A 1% error at the beginning becomes a 1% error everywhere, and 1%, when applied to the age of the universe, is roughly 140 million years. Longer than the entire Cretaceous period, longer than the time from the first dinosaurs to the last. Let that sink in. The precision of our cosmic timeline depends on our ability to measure the true brightness of a pulsating star, a star whose brightness is constantly changing, in a galaxy filled with dust that dims and reddens the light, and to distinguish that star from other pulsating stars that look similar but are fundamentally different. We live in an era of extraordinary measurement capability. We can detect gravitational waves from merging black holes more than 1 billion light-years away, ripples in the fabric of space-time itself, with amplitudes smaller than 1,000th of the diameter of a proton. We can measure the temperature of the cosmic microwave background radiation to 1 part in 100,000, mapping the subtle temperature variations that encode the seeds of all cosmic structure. We can time the pulses of millisecond pulsars to nanosecond precision, turning spinning neutron stars into the most stable clocks in the universe. And yet, when it comes to the most fundamental measurement in cosmology, how fast the universe is expanding, we cannot agree on the answer to better than about 8%. Two teams, using two different but equally rigorous methods, arrive at answers that differ by roughly 6 kilometers per second per megaparsec. This discrepancy, the Hubble tension, is not a minor quibble about the last decimal place. It is a fundamental disagreement about the basic properties of the cosmos. It affects our estimate of the universe's age by nearly 1 billion years. It affects our understanding of the density and composition of the universe. It may affect our picture of how dark energy behaves over cosmic time. This is not science fiction. This is the actual state of affairs in early 21st century cosmology. We have reached a precision in our measurements where the remaining uncertainties are no longer merely technical. They are foundational. They touch the bedrock assumptions on which the entire edifice of modern cosmology is built. And the foundation begins with Cepheids. Consider what it means to measure the distance to a Cepheid in a galaxy 50 million light-years away. The light from that star left the galaxy 50 million years ago, during the Eocene epoch on Earth, when the planet was warm and covered in subtropical forests, when early primates were beginning to diversify, and the first whales were evolving from land-dwelling mammals. That light has been travelling through the expanding void of intergalactic space for 50 million years, its wavelength slowly stretching as space itself expands, its intensity diminished by every wisp of dust it passed through, its signal mixed with the light of every other star in the galaxy. At the end of its 50 million year journey, the light enters the optics of a telescope, perhaps the James Webb Space Telescope, orbiting the Sun at the second Lagrange point, 1.5 million kilometers from Earth. The light is collected by a mirror 6.5 meters across, focused onto an infrared detector, and converted to electronic signals. Those signals are transmitted back to Earth, processed by computers, and analyzed by a team of astronomers who must extract, from the noisy, blurred data, the pulsation period of a single star among hundreds of millions of other stars in the same field. The fact that we can do this at all is a testament to human ingenuity of the highest order. The fact that we can do it with sufficient precision to make meaningful statements about the expansion rate of the universe is astonishing. But the margins are thin. Every correction matters. Every assumption carries weight. Every source of systematic error must be identified, quantified, and removed, or at least bounded. And this brings us back to Delta Cephei itself, the prototype. Delta Cephei is not just a historical curiosity, a relic of 18th century astronomy preserved in the name of a class of stars. It is still one of the most intensely studied stars in the sky, a laboratory for testing the physics of stellar pulsation and the calibration methods that underpin the entire distance ladder. Every improvement in observational technology gets applied to Delta Cephei first. Every new technique for measuring stellar distances gets tested against it. The star has become a benchmark, a standard against which all other Cepheid measurements are compared, and yet even this benchmark retains stubborn uncertainties that no amount of observation has fully eliminated. There is something philosophically fascinating about this situation. We have a star that we can see with the naked eye, a star located within our own galaxy, a star that has been observed more or less continuously for nearly 250 years. And we still cannot agree on precisely how far away it is, or precisely how luminous it is. The measurements are excellent by any historical standard, but excellence is not the same as certainty. And in cosmology, where small errors amplify over vast distances, the difference between excellence and certainty matters enormously. Modern observations have refined our understanding of its physical properties to extraordinary precision. Its pulsation period is 5.366341 days, measured across more than 2 centuries of continuous observation, a baseline that spans from the late 18th century to the present day. Its surface temperature oscillates between roughly 5,500 Kelvin at minimum light, when the star is contracted and coolest, and about 6,800 Kelvin at maximum light when it is expanded and hottest. Its radius changes by roughly 10% over each cycle, from about 40 solar radii at minimum to roughly 44 solar radii at maximum. In 2012, astronomers using the CARA array, a network of 6 optical telescopes on Mount Wilson, linked together as an interferometer, directly resolved the pulsation of Delta Cephei. For the first time in history, someone watched a Cepheid variable physically swell and shrink. They measured the angular diameter of the star's disk at different phases of its pulsation cycle, and found that the angular size changed in precisely the way predicted by pulsation models. By combining these angular diameter measurements with spectroscopic measurements of the star's surface velocity, the rate at which the surface is expanding or contracting along the line of sight, they could determine the physical size of the star at different phases. Comparing the physical size to the angular size gives the distance, a technique known as the Bardy-Wesselink method, or more precisely, the interferometric Bardy-Wesselink method. The distance they obtained for Delta Cephei was approximately 860 light-years, with an uncertainty of about 10%. This result was broadly consistent with other estimates, including the Hipparcos parallax measurement, but the uncertainty remained substantial, even for this single, well-studied, intensely observed star, the prototype of its entire class. We do not know the distance to better than roughly 10%. If we cannot pin down the distance to Delta Cephei itself, a star in our own galaxy, a star we have been observing for nearly 250 years, to better than 10%, what does that say about our confidence in distances to Cepheids in galaxies millions of light-years away? The answer is that we can be reasonably confident but not certain. The cosmic distance ladder is statistically robust. When you observe hundreds of Cepheids in a distant galaxy, the individual measurement errors average out and the distance estimate becomes more precise. But systematic errors do not average out. If there is a systematic bias in the extinction corrections, or the metallicity corrections, or the zero-point calibration, it affects every Cepheid in the same direction. It tilts the entire ladder, and a tilt of even 1 or 2%, amplified across billions of light-years, can have profound consequences for our picture of the universe. Let that sink in. The difference between a universe that is 12.9 billion years old and one that is 13.8 billion years old, a difference of 900 million years, may hinge on whether we have correctly accounted for the reddening effect of interstellar dust on a few hundred pulsating stars in a handful of galaxies within 100 million light-years of Earth. There is a concept in philosophy of science called the Duhem-Quine thesis. It states that any scientific hypothesis is always tested in conjunction with a web of auxiliary assumptions, and that when an observation disagrees with a prediction, you cannot be sure which assumption is wrong. The hypothesis might be wrong, or any one of the auxiliary assumptions might be wrong, or several might be wrong in ways that partially compensate for each other. The Hubble tension is a textbook example of this principle in action. Is the problem with the Cepheid calibration, with the supernova standardization, with the analysis of the cosmic microwave background, with the lambda CDM cosmological model, with the nature of dark energy, with the number of neutrino species, with some piece of physics we have not yet imagined? All of these possibilities are being actively investigated, and the resolution, when it comes, will likely reshape our understanding of the universe as profoundly as Barday's 1952 correction reshaped it, or as Hubble's 1925 announcement reshaped it before that. Meanwhile, Delta Cephei continues to pulsate. It does not care about our theories. It does not care about our confusion. It has no stake in the outcome of the Hubble tension. It simply swells and contracts, brightens and dims, as it has done for millions of years, and will continue to do for millions more, until the hydrogen and helium in its interior are exhausted, until nuclear fusion can no longer sustain it, until it swells one final time into a bloated red supergiant, and then, depending on its exact mass, either sheds its outer layers as a planetary nebula, leaving behind a white dwarf, or collapses and explodes as a supernova, scattering its elements into the void. The star was here before us. It will be here after us. Our understanding of it is a temporary artifact, a model that we hold up against the sky and adjust when the fit is poor. The fit is currently poor. Something does not match. And the history of astronomy suggests that when the mismatch is resolved, the resolution will surprise us. It always does. There is a deep, almost vertiginous humility in this realization. We have built a tower of inference that reaches from the surface of a pulsating star in our own galaxy to the edge of the observable universe, 93 billion light-years of distance, spanned by a chain of reasoning that is brilliant, elegant, and fragile. The tower is one of the greatest intellectual achievements of our species, but it sways, it creaks, it rests on a foundation that we are still excavating, still testing, still debating. Consider how many individual steps are required to go from Delta Cephei to the Hubble constant. First, you measure the parallax of Delta Cephei, or another nearby Cepheid, giving you a geometric distance. That measurement depends on the calibration of the Gaia spacecraft's astrometric instruments, on the correction for systematic effects in the astrometric solution, on the proper treatment of binary companions, and on the statistical handling of the parallax 0 point. Second, you use that geometric distance, combined with the star's apparent brightness and pulsation period, to anchor the period-luminosity relationship. That step depends on accurate photometry, accurate extinction corrections, and the assumption that the star is pulsating in the fundamental mode rather than an overtone. Third, you apply the calibrated relationship to Cepheids in other galaxies, measuring their periods and apparent brightnesses and calculating their distances. That step depends on the universality of the period-luminosity relationship, on accurate extinction corrections in the host galaxy, on the correct identification of the stars as classical Cepheids rather than Type II Cepheids, and on the absence of blending with unresolved neighboring stars. Fourth, you use those galaxy distances to calibrate Type 1a supernovae. Fifth, you use the supernovae to measure distances to the most remote galaxies and determine the expansion rate. Each step is well understood. Each step has been scrutinized, tested, and refined by some of the most brilliant minds in science. And yet the end result, the Hubble constant, differs by 8% from the value obtained by an entirely independent method. Something in the chain is not quite right, or the independent method is not quite right, or both are slightly off, or there is new physics that neither method accounts for. The resolution will come. It always does, but it has not come yet. And the waiting is itself a form of knowledge, a recognition that the universe is not finished revealing itself, that there are still surprises hiding in the data, that the story of Delta Cephei and its descendants is not yet complete. And at the very bottom of that foundation, supporting everything, is a heartbeat, a gentle, rhythmic heartbeat of light from a star that no one thought was special, in a constellation named after a mythological king, noticed by a boy who could not hear the world but who could see, with perfect clarity, the flickering of the stars. The history of the Cepheid distance scale is, in a very real sense, a history of humility. Every generation of astronomers has believed that they finally got the calibration right. Shapley believed it, Hubble believed it. The post-Babe generation believed it. The Hubble Space Telescope Key Project team believed it. And each time, the next generation found errors that the previous one had missed. Not because the previous generation was incompetent, far from it, but because the universe is more complex than any single generation can fully appreciate. In Shapley's era, no one knew there were two types of Cepheids. In Hubble's era, no one fully appreciated the extent of interstellar extinction. In the mid-20th century, no one suspected that metallicity might affect the period-luminosity relationship. In the early 21st century, we are grappling with the possibility that even our most careful calibrations, using the best space telescopes ever built, might still harbour systematic effects that we have not identified. The pattern is clear. Every advance in technology reveals a new source of error. Every improvement in precision uncovers a new subtlety. The universe refuses to yield its secrets cheaply. It demands that we work harder, measure more carefully, think more critically, and remain open to the possibility that we are wrong. There is a parallel to the star itself. A Cepheid variable pulsates because it is out of equilibrium. The helium ionization zone in its interior is constantly trying to reach a stable state and constantly failing. It overshoots, then undershoots, then overshoots again. The pulsation is not a sign of disorder. It is a sign of a system trying and failing to balance competing forces. In the same way, our understanding of cosmic distances pulsates. We revise upward, then downward, then upward again. We overshoot and undershoot. We are constantly trying to reach the truth and constantly finding that the truth is more complicated than we assumed. This pulsation of knowledge is not a flaw. It is a feature. It is the rhythm of science itself, the heartbeat of a system that is alive, dynamic, and self-correcting. A system that is dead would not pulsate. It would sit still, confident, and wrong. A system that is alive oscillates around the truth, getting close with each cycle, never quite arriving, always adjusting. The question that hangs over modern cosmology is whether the current oscillation, the Hubble tension, is a minor adjustment or a major correction. Are we in a barred moment on the verge of a recalibration that will once again double or halve our picture of some fundamental quantity? Or are we approaching convergence, closing in on the true value of the Hubble constant from multiple directions, with the remaining discrepancies explained by subtle and mundane systematic effects? No one knows. And that uncertainty, that genuine, irreducible not knowing, is one of the most exciting things about being alive at this particular moment in the history of science. We are watching one of the oldest and most important measurements in astronomy, the measurement of cosmic distance, undergo a real-time stress test. The tools are better than they have ever been. The data is more abundant than it has ever been. And the answer is more uncertain than it has been in decades. Something will give. Something always does. And when it does, the story of Delta Cephei will gain another chapter, another correction, another moment of clarity that makes the previous understanding look incomplete. It has happened before. It will happen again. The heartbeat continues. What does it mean that our map of the universe rests on such delicate foundations? What does it mean that the distances we quote with confidence, the numbers we print in textbooks and display in planetariums, are the products of a chain of reasoning that stretches back to a single observation made in 1784 by a teenager in a garden? It means, first, that science is not a collection of facts etched in stone. It is a process, a living, breathing, evolving process of successive approximation, of getting less wrong over time. The history of the Cepheid distance scale is a history of corrections. Hubble's original distance to Andromeda was wrong by a factor of 3. Beatty's correction doubled all extragalactic distances. Subsequent work by Sandage, Tamman, Friedman and Rias refined the scale further, each generation finding errors that the previous generation had missed, each correction bringing us closer to the truth, but never quite reaching it. This process of correction is not a sign of weakness, it is a sign of strength, a system of knowledge that actively seeks out its own errors, that rewards the discovery of mistakes, that treats every measurement as provisional and every certainty as temporary, is far more powerful and far more trustworthy in the long run than one that claims perfection. The Cepheid distance ladder has been wrong multiple times, and each time the scientists who used it identified the error and corrected it. This self-correcting capacity is what distinguishes science from dogma. Dogma asserts and defends. Science measures, tests, and revises. The two processes may look similar in the short term, but over decades and centuries, they diverge profoundly. But there is a philosophical dimension to this story that goes beyond methodology, that touches something deeper about the relationship between human beings and the universe we inhabit. The Cepheid distance ladder tells us that we did not measure the size of the universe directly. We inferred it. We built a chain of reasoning, link by link, from the nearby to the distant, from the geometric to the physical, from the visible to the invisible. Each link is an act of interpretation. Each link depends on the others. The distances are not given to us by nature. They are constructed by us through observation, calculation, and assumption. The universe does not come labelled. It does not put up signposts that say Andromeda, 2.5 million light-years. We impose those numbers. We derive them through a process that involves real observations of real objects, real physics, real mathematics, but also real uncertainties, real assumptions, and real opportunities for error. The numbers are the output of a system. The system is remarkable, but it is human, and human systems can be wrong. This is not a counsel of despair, it is a counsel of humility. The distances we measure to galaxies are probably approximately correct. The Hubble constant is probably somewhere between 67 and 73. The age of the universe is probably between 12.5 and 14 billion years. These are not wild guesses. They are the best estimates that the finest minds and instruments in the world can produce. But they are estimates. They are provisional. They are subject to revision. And the history of the field teaches us that revision is not an abstract possibility. It is a near certainty. Consider the people who made this story possible and what their lives tell us about the human side of cosmic discovery. John Goodrick, deaf since childhood, spending long winter nights observing the stars from exposed gardens and rooftops, unable to hear the sounds of the world around him, but able to see, with extraordinary clarity and patience, the subtle variations in starlight that others had missed. He died at 21. He never knew that his observation of a flickering star would lead to the discovery that the universe is expanding. He never knew that his name would be attached to a class of variable stars that would become the most important distance indicators in astronomy. Henrietta Swan Leavitt, working for pennies per hour in a room at Harvard, denied access to the telescopes, denied authorship of her own publications, her health declining from the disease that would eventually take her hearing, just as it had taken Goodricky's. She discovered the period-luminosity relationship, one of the most consequential findings in the history of science, and published it under her director's name. When the Swedish mathematician Gösta Mittag-Leffler wrote to the Harvard Observatory in 1926 to nominate Leavitt for the Nobel Prize in Physics, he was informed that she had died of cancer 4 years earlier in 1921 at the age of 53. Nobel Prizes are not awarded posthumously. Her discovery went unhonoured in her lifetime. The period-luminosity relationship is now sometimes called the Leavitt law, a belated recognition that came far too late. Walter Baade, a German immigrant working in the United States during a world war, using the accidental gift of dark skies over wartime Los Angeles to look deeper into Andromeda than anyone had looked before. He found the error that doubled the universe. He stood before the assembled astronomers of the world in Rome and told them, calmly and factually, that every extragalactic distance they had ever published was wrong by a factor of 2. He did not apologize. He did not celebrate. He simply presented the data and let the implications speak for themselves. Edwin Hubble, driven and ambitious, building on the work of Leavitt, Slipher, Humason, and others, often without generous acknowledgement. He discovered the expansion of the universe, one of the most profound findings in all of human thought, and spent the rest of his career refining the measurement, never fully satisfied, always aware that the numbers might change, always pushing for greater precision. These were not demigods. They were people. They had flaws, ambitions, rivalries, insecurities. They made mistakes. They sometimes took credit that belonged to others. They died before their contributions were fully recognized. And yet, across decades and continents, often working independently, often not fully aware of each other's contributions, they built something magnificent. They built a system of measurement that spans the cosmos, a ladder that reaches from a garden in York to the edge of the observable universe. There is a metaphor embedded in the Cepheid variable itself that resonates with the story of human inquiry. The Cepheid pulsates, it swells and contracts, it brightens and dims. It is perpetually out of equilibrium, perpetually oscillating between two states, never settling, never resting. Science does the same. Scientific understanding expands with new discoveries, contracts when errors are found, then expands again. The rhythm is not smooth. It is messy, contentious, sometimes painful. Careers are staked on one side or another of a disputed measurement. Papers are published and rebutted. Conferences become battlegrounds. But the oscillation continues. The heartbeat does not stop. We are temporary creatures on a temporary planet, orbiting a temporary star, in a galaxy that will eventually merge with its neighbor and lose its identity in the process. If the age of the universe were compressed into a single calendar year, all of recorded human history, every war, every poem, every telescope, every theory, would occupy roughly the last half second of December 31st. We are a flash, a momentary flicker of consciousness in a cosmos that is overwhelmingly empty, overwhelmingly dark, and overwhelmingly indifferent to our existence. And yet we looked it up. We saw a star change. We measured the change. We used the measurement to reach across millions of light years and determine the distance to other galaxies, the speed of the expansion, the age of everything. We started with one blinking point of light in the constellation Cepheus, and we ended up with a map of a universe 93 billion light-years across, containing 2 trillion galaxies, expanding into an unknown future that we are only beginning to imagine. That is what one pulsating star gave us. Not certainty, not final truth, not the last word, but a method, a ladder, a way to extend our reach beyond the horizon, to measure what cannot be touched, to know what cannot be visited. The star did not give us answers. It gave us a way to ask better questions, and perhaps that is enough. There is one more implication worth considering, one that rarely appears in the scientific literature, but that haunts the edges of every conversation about cosmic distance. It is the implication for our sense of place. For most of human history, we believed we were at the center of everything. The Earth was the center of the cosmos. The sun orbited us. The stars were fixed to a sphere that enclosed us. Everything revolved around us, literally and figuratively. Then Copernicus displaced us from the center of the solar system. Then Shapley displaced us from the center of the galaxy. Then Hubble displaced us from the center of the universe by showing that the universe has no center, that every point in it is receding from every other point, that there is no special location anywhere. Each displacement was painful. Each one diminished our sense of cosmic importance, and each one was made possible, in part, by better measurements of distance, by better understanding of how far away things are, and therefore how big we are relative to them. The Cepheid distance scale is the instrument of our most profound displacement. It told us that the Milky Way is just one galaxy among trillions. It told us that the nearest galaxy is not a few thousand light-years away, as Shapley had estimated, but 2.5 million. It told us that the universe is expanding, that it had a beginning, and that its future is defined by forces we do not understand. Every one of these revelations came from the same source, from the period-luminosity relationship, from Leavitt's law, from the breathing of a star. If you compress the size of the observable universe down to the scale of the Earth, our galaxy would be smaller than a single grain of sand on a vast beach. Our solar system, on that scale, would be invisible, smaller than an atom. A bacterium on the grain of sand would be immeasurably larger than our entire world. And yet that invisible, atom-sized solar system is where all of this happened. All of the observations, all of the calculations, all of the debates, all of the corrections. Every Cepheid ever measured, every distance ever computed, every version of the Hubble constant ever published, All of it originated on a mote of dust, orbiting a forgettable star in the outer suburbs of an unremarkable galaxy. The scale is crushing, but it is also, strangely, liberating. Because the fact that we know the scale, the fact that we can comprehend it, even if we cannot feel it viscerally, the fact that we can hold in our minds the number 93 billion light-years and understand what it means, even imperfectly, that is something. That is not nothing. A universe that contains beings capable of measuring it is a different kind of universe from one that does not. And we are those beings. Small, brief, fragile, confused, and capable against all odds of measuring the distance to the stars. The Cepheid variable is our measuring rod. It is the tool we crafted from the physics of stellar interiors and the patience of human observation. It is imperfect. It has led us astray before. It may be leading us astray now. But it is the best we have. And the fact that it exists at all, that the universe happens to contain a class of stars whose pulsation period is directly linked to their intrinsic brightness, a relationship that was not inevitable, not required by any fundamental principle, just a fortunate consequence of the way helium ionization zones interact with stellar structure. That fact is itself a kind of gift. The universe is not obligated to be measurable, but it is, at least partially, at least approximately, at least enough for us to know how little we know. Delta Cephei is still there. Tonight, if you are in the northern hemisphere and the sky is clear, you can find it. Look toward the north. Find the constellation Cepheus, which looks like a rough, lopsided house shape, near the familiar W of Cassiopeia, and the bright North Star, Polaris. Delta Cephei is at one corner of this house, not the brightest star in the figure, not the most prominent, but there. A modest point of light, unremarkable to the casual eye. You would never pick it out as extraordinary. You would never guess, looking at it, that this particular pinprick of light holds the key to the size of the universe. If you watch it over several nights, and you know where to look and what to compare it to, you can see its brightness change with your own eyes. At maximum brightness, Delta Cephei shines at about magnitude 3.5, easily visible from a suburban backyard. At minimum, it dims to about magnitude 4.4, still visible but noticeably fainter. The change is roughly one full magnitude, a factor of about 2.5 in brightness. If you compare Delta Cephei to the nearby star Zeta Cephei, which does not vary and serves as a convenient reference point, you can watch the prototype Cepheid variable brighten and dim over the course of a week, following the same rhythm that Goodrick measured in 1784. You will be seeing, with nothing more than your own unaided eyes, the same phenomenon that launched the measurement of the cosmos. There is something profound about that connection. The light entering your eyes has travelled roughly 860 light-years. It left the star around the time of the medieval Crusades. It carries within it, encoded in its intensity and colour, information about the physical state of a supergiant star pulsating under the influence of forces that operate deep below its photosphere. And you, standing on the Earth, are decoding that information by the simple act of looking up and noticing that the star is a little brighter tonight than it was 3 nights ago. But it does. Or rather, it did, and in many ways it still does. Delta Cephei is the prototype, it is the original. It is the star that defined a class, that gave its name to a phenomenon, that launched a chain of discovery stretching across 2 centuries and reaching to the farthest corners of the observable cosmos. Every Cepheid variable discovered since 1784 is, in a sense, an echo of Delta Cephei. Every distance, measured using the period-luminosity relationship, is a descendant of the observation that John Goodrick made in a garden in York 242 years ago. The star does not know this. It has no awareness. It has no memory. It is a ball of gas, roughly 42 solar radii in diameter, roughly 5 solar masses in weight, burning hydrogen and helium in its core, pulsating with a period of 5.37 days, because the physics of its interior demands it. It is doing what physics requires, nothing more, nothing less. And yet the accident of its pulsation, the fortunate coincidence that the kappa mechanism in its helium ionization zone produces a stable, repeating, measurable rhythm, has given our species one of its most powerful tools for understanding the cosmos. There is a term that astronomers use for the period-luminosity relationship. They call it the Leavitt law. This name is a correction, a belated one. For decades, the relationship was attributed to Pickering or to the observatory as a whole, or simply described without attribution. Leavitt's contribution was acknowledged in footnotes, if at all. She was a computer, a human calculator, a woman doing work that the men around her considered beneath them. Her genius was treated as labor. Her insight was treated as a byproduct of tedious cataloguing. But it was not. The period-luminosity relationship was not hiding in the data, waiting to be noticed by anyone with sufficient patience. It required a particular kind of intelligence to recognize, a sensitivity to pattern, an ability to see order in what appeared to be noise. Leavitt looked at photographic plates showing thousands of variable stars in the Magellanic Clouds, and she saw what no one else had seen. She saw that the brightness and the period were linked. She saw that the link was clean, consistent, and meaningful. She saw in the flickering of distant stars the outline of a cosmic ruler. The Leavitt law is sometimes described as the most important relationship in extragalactic astronomy. This is not an exaggeration. Before the Leavitt law, we had no way to measure distances beyond a few hundred light-years. After the Leavitt law, we could reach millions of light-years. Before the Leavitt law, we did not know whether the spiral nebulae were part of our galaxy or separate galaxies in their own right. After the Leavitt law, we knew they were separate. Before the Leavitt law, we did not know the universe was expanding. After the Leavitt law, applied through the work of Hubble and others, we knew it was. The expansion of the universe, the Big Bang, the age of the cosmos, the existence of dark energy, all of these discoveries trace back, through a chain of inference, to the relationship that Leavitt found. One woman, 25 data points, a graph, and the universe opened up. The story of the Cepheid distance scale carries within it a lesson about the nature of knowledge that extends beyond astronomy, beyond science, into the realm of philosophy and human experience. The lesson is this: all of our knowledge of the distant is built from the nearby. All of our understanding of the vast is constructed from the small. We cannot go to the galaxies. We cannot visit the cosmic microwave background. We cannot stand at the edge of the observable universe and look outward. We can only sit on our small planet, look up and reason we do. We reason from parallax to Cepheids, from Cepheids to supernovae, from supernovae to the Hubble flow. Each step is a leap, a carefully calculated leap, grounded in physics and mathematics, but a leap nonetheless. Each step takes us further from the solid ground of direct measurement and deeper into the realm of inference. At the base of the ladder, we can touch what we measure. We can point to the sky and say, this star moved by this many arcseconds over 6 months, and therefore it is this far away. At the top of the ladder, we are dealing with abstractions, with corrections and models and statistical analyses, with objects so far away that the light we observe left them when the universe was a fraction of its current age. The audacity of this enterprise is staggering. The fragility of it is humbling. And the fact that it works, that it gives us answers that are mostly consistent, mostly self-reinforcing, mostly coherent, is one of the great intellectual achievements of our civilization. Mostly. That word is important. Mostly consistent, mostly coherent, not perfectly, not completely. The Hubble tension reminds us that mostly is not entirely. The gap between 73 and 67 is a gap that matters. It is a gap where new physics might live, or it is a gap where an old error might hide. We do not yet know which, but the search continues. New telescopes come online, new techniques are developed, new data accumulates. The Vera C. Rubin Observatory, named after the astronomer who provided some of the most compelling evidence for dark matter, will begin surveying the southern sky and is expected to discover thousands of new Cepheids in the Milky Way and the Magellanic Clouds. The James Webb Space Telescope continues to observe Cepheids in ever more distant galaxies, pushing the reach of the distance ladder farther into the void. The Gaia spacecraft continues to refine its parallax measurements, tightening the geometric anchor at the base of the ladder. Each new observation is a test. Each new measurement is an opportunity for the chain to break or to hold, and so far, despite decades of scrutiny, the chain has held. It has bent, it has stretched, it has shown cracks that turned out to be artifacts, and cracks that turned out to be real, but it has not broken. The Cepheid distance ladder is still the primary route from here to there, from our galaxy to the cosmos, from a single blinking star to the edge of everything. There is poetry in the pulsation. There is meaning in the rhythm. Not cosmic meaning, not the kind of meaning that the universe imposes on us, but the kind of meaning that we impose on the universe. The kind of meaning that arises when a conscious being looks at an unconscious cosmos and sees in it a reflection of its own deepest concerns. Impermanence, rhythm, the desire to measure what cannot be held, the drive to understand what cannot be fully understood, the courage to build a chain of reasoning across billions of light years and to trust it, tentatively, provisionally, with the full knowledge that it might break. Delta Cephei pulsates. It has pulsated for millions of years. In roughly 10 to 20 million years, give or take, it will exhaust the fuel in its core and evolve off the instability strip, the narrow region of the Hertzsprung-Russell diagram, where Cepheid pulsation is possible. It will swell into a larger, cooler star. Its pulsation will cease. Its heartbeat will stop. The prototype will die, and only the name will remain, attached to a class of stars that span galaxies. But by then, if humanity survives, we may have built new ladders. We may have found new standard candles, new methods, new ways to measure the distances between the stars and the galaxies, and the great walls and voids that define the large-scale structure of the cosmos. We may look back at the Cepheid distance scale the way we look back at Ptolemaic astronomy, with respect for its ingenuity and amusement at its limitations. Or we may find that the Leavitt law, refined and corrected and extended, remains the bedrock of cosmic cartography for centuries to come. There is no way to know. What we can know is this. Right now, tonight, a star in the constellation Cepheus is brightening. It is approaching the peak of its cycle. Its outer layers are swelling outward, driven by the rhythmic pulse of the Kappa mechanism in its helium ionization zone. In a few days, it will reach maximum brightness, and then it will begin to fade. Then it will brighten again, then fade, then brighten. The cycle will repeat. The heartbeat will continue. 242 years ago, a young man who could not hear the world looked up at that star and noticed something that no one had ever noticed before. He noticed that it changed. He wrote it down. He measured it. He reported it. And then he died, at 21, in the cold of an English spring, never knowing that his observation would lead to the discovery that the universe is vast, that it is expanding, and that the darkness between the galaxies is filled with forces we cannot see and do not understand. Henrietta Leavitt took what Goodrick found and turned it into a tool. She saw the pattern that connected period to brightness. She wrote it up, she published it, and then she died at 53, her work credited to others, her name nearly lost to history, never knowing that her discovery would be called one of the most important in all of astronomy. Walter Beatty took what Leavitt found and corrected it. He distinguished between two types of Cepheids that everyone else had confused. He doubled the size of the universe. He stood before the world's astronomers and told them they were wrong. And then he returned to his telescope and kept looking. Edwin Hubble took what all of them found and used it to prove that the spiral nebulae were separate galaxies. He used it to discover the expansion of the universe. He used it to reshape humanity's picture of the cosmos more profoundly than any single person since Copernicus. And even he got the numbers wrong by a factor of 3 because the chain of reasoning that connected his telescope to the stars of Andromeda was not yet strong enough to bear the weight of the truth. The chain is stronger now, but it is still not perfect. It may never be perfect, and perhaps that is the point. Perhaps the value of the chain lies not in its perfection, but in the act of building it. Perhaps the value of the Cepheid distance scale lies not in the final number it produces, whether that number is 67 or 73, but in the process of refinement, the endless, patient, humbling process of measuring, correcting, measuring again, and inching closer to a truth that we will never fully possess. The universe is under no obligation to reveal itself to us. It is under no obligation to provide stars that pulsate with periods proportional to their luminosity. It is under no obligation to make itself measurable, comprehensible, or knowable. And yet it does, partially, imperfectly, grudgingly. It gives us Cepheids. It gives us the Leavitt law. It gives us enough information to construct a distance scale, to estimate an expansion rate, to infer an age. And then it gives us a tension, a discrepancy, a crack in the foundation, just enough to remind us that our understanding is incomplete, that the story is not over, that there is always more to learn. Somewhere tonight, 890 light years from here, a star is breathing. Its light is traveling toward us across the void, crossing the emptiness between the stars, carrying with it the encoded message of its own rhythm. In 5 years, in 50 years, in 500 years, that light will arrive at a telescope, and someone will measure it, and someone will use that measurement to update a number, and someone will argue about what the number means. The heartbeat will continue. The chain will stretch a little further, and the question that John Goodrick first asked, in a garden in York, under a cold northern sky, the question of how far away the stars are and what their flickering means, will remain, as it has always been, one of the deepest and most beautiful questions that a human being can ask. The stars do not answer, they only pulse, and in their pulsing we find not answers, but the next question, and the next, stretching outward, like light itself, into the dark.